Before we add new content to our knowledge base, let's first go over what we've learned in the previous couple of weeks. So the first question is pretty basic. We want to know what these R's mean. So we have the small r's and then we have the large R's. And the small r's give us an association between two variables, just in the bivariate case. So the little r tells us the strength of an association between an x and a y variable. And recall that the absolute value tells us the strength of the relationship, and then the sign tells us the direction. If we square that number, we get the r squared, little r squared, which is an effect size, and it gives us the proportion of variance that is explained in y by x and vice versa. Okay, so it gives us that proportion of variance explained. The large r's are for the multivariate case, where we have two or more predictors in explaining variance in a DV of interest. And so the large R is the strength of the association between the DV and an optimally weighted combination of predictors. And if we square that, we have the proportion of variance explained in the DV by an optimally weighted combination of predictors. And both R squareds are indicators of an effect size. The proportion of variance explained specifically. The second one, what does the B weight represent and the beta weight? Well, what they both have in common is that they're a measure of the slope of the best fitting line. So for the B weight, that's the unstandardized slope, or the raw unit. So as we move 1 unit increase in a predictor, what do we expect the DV to do? How do we expect it to change? So again, if the slope is negative, if the B weight is negative or the beta weight, that means that we have a negative association there, negative slope. And if it's positive, then we have a positive. And for the beta weight, it's very similar, except that it's in the standardized unit. So as we increase the predictor by 1 standard deviation, what change do we expect in the DV? So that's what those two things represent. If they are significant, that means that, and they both will be significant or they both will not be significant. One can't be significant without the other. And that just means that we expect a significant change in the DV based on that 1 unit increase in the predictor. What is the formula for B in the one predictor case? Recall that that is the R, so the little r, and that would be multiplied by the fraction of the standard deviation of y over the standard deviation of x. So that's a quick way to get the B weight. What is the formula for the beta in the multiple predictor case, specifically in the 2 predictor case? I will never ask you to think about more than 2 predictors when we're thinking of B weights. So the formula for that, recall, is the correlation between the DV and the first predictor. So remember that was RY1, or just R1. And then we're going to subtract off of that the product of the of 2 things. Remember the correlation between Y and predictor 2, and then the correlation between the 2 predictors. Remember that was R12. And then the denominator of that, so we're going to divide that by 1 minus R12 squared. And that's going to be on the denominator. So we're going to touch on this formula again in this lecture, and the goal is for us to understand what happens when that R12 increases. What happens to the whole formula? What happens to beta? What is the purpose of regression? Well, the purpose of simple regression, remember in the two variable case or the bivariate case, is we want to know what will happen to the DV based on the knowledge of a predictor variable's value. Okay, so what is the expected, more specifically, what is the expected value of a DV when we have knowledge of the value of a predictor variable? And the purpose of multiple regression, again 2 or more predictors, is we want to understand the expected value of the dependent variable based on knowledge of an optimally weighted combination of those predictors. Okay, so you can kind of see a pattern here in the answers, right? So the purpose of regression, and overall, in the bigger scheme of things, the purpose of regression is prediction, always prediction. Compare ANOVA and regression. So ANOVA technique and regression have some similarities, and there will always be an ANOVA table in ANOVA analysis and in regression analysis, so that's kind of interesting. The ANOVA table is helpful for both. But the methods themselves, you'd use them differently. So ANOVAs are great for categorical predictors. When you're looking at mean differences across different groups on a DV, then a one-way ANOVA is appropriate. Regression it also does that well, but you'd have to do some coding for that if there are if there are more than two groups. So we'll cover that later in this course. Regression handles nonlinearity very well. So if we're expecting a curvilinear relationship, I think we'll cover that next week. ANOVA can't handle that. Regression can handle categorical predictors and continuous predictors in the same analysis. So if you were looking at different departments, wanting to predict differences between people from different departments and understanding that, and plus you would want to understand their conscientiousness levels or other kinds of continuous predictors, individual difference kinds of variables, you could put both of those in the same equation with some coding for the categorical variable, like what department the person is from, and you would be able to use regression for that, but you couldn't use ANOVA. Maybe you could use an ANCOVA, but I think regression is probably the better way to go. Other differences between them. Regression handles dichotomous DV, and ANOVA doesn't. So when we have a dichotomous DV like a person's guilt or innocence, or the probability of contracting some kind of disease or having some kind of issue, those kinds of dichotomous DVs or outcomes are handled with regression much better than ANOVA. Remember the the cell sizes, remember the n's for the different cells in ANOVA, they have to be equal or should be equal. For regression, that's not as big a deal. So overall, regression is more flexible technique and can handle various kinds of predictors much better. Oh, and one more thing. Regression also can partition variance much better than ANOVA can. We can see unique variance accounted for by certain predictors much better, and also regression accounts for correlations among the different predictors. So it's just a much better technique overall for the most part. It depends on what analysis you're doing. ANOVA can still be good. One ways I think are used probably the most when we just have like 4 different departments, for example, and we're trying to figure out if the sales differed across those 4 departments. That would be a one-way ANOVA. That would be an easy one where we wouldn't want to use regression probably for that. But more on that to come. So just thinking through these things, you'll learn more as we progress about when we would use different analyses to answer different kinds of questions. Next, what does the intercept tell us in a simple regression equation? Well, the intercept, or the B naught, is the expected value of the DV when the predictor is set to 0. And in a multiple regression case, that is the expected value of the DV when all predictors are set to 0. And so if 0 doesn't make sense for that predictor, remember like GRE scores, who gets a GRE score of 0, right? Well, that's when we would want to center the predictor variable. We don't usually center the DV, recall. But centering the predictor is helpful for interpretation. So we're going to make the mean the 0, and then that will make automatically the y-intercept the mean of the DV. So that's why centering is important, is because it aids in prediction, and this will come up again and again through the stat sequence. Centering is used quite frequently for this purpose, particularly in multi-level modeling, which comes later. So I want you to know what it is and why it's done, and know that it makes the intercept change to the mean of the DV.